All right. Hey everybody, my name is Thomas Martin, and today I will be discussing the Wiggers diagram. It seems a little complicated at first. On first glance, there's a lot going on, but my goal with this video is just to break it down and make it a little bit simpler for you. So I'm going to go ahead and give a disclaimer. I am very sick right now, so if I'm super stuffy or sniffling or coughing, just do your best to ignore that. But anyway, let's get into it. So Wiggers diagram. Go here, and here is the actual graph that we're going to be looking at today. So, like I said, it's a lot at first, but once you start to break it down and get into like each component of what's going on, it's really not that much. And it makes a lot of sense as to why all of this goes together. So we're going to kind of break it down line by line, section by section, just show you what's going on. The way that I like to think of the Wiggers diagram, or what it really is, I guess, is a timeline of what is happening within the heart. So we can see the seconds down here, and that's telling us when everything is happening within the heart. And as we go up the graph, it's going to tell us what is happening within the heart. So it's kind of a timeline of how things interact, how pressure changes affect certain parts, how the EKG shows us what's happening, and then how the volume changes as well. So we're going to go ahead and get into the different parts. Real quickly, I'm going to explain each of these three parts, and we're going to break them down. So first, let's go pressure. Pressure we'll do in blue. So this is pressure right here. So anytime I'm talking about pressure, you're going to look to this part of the graph, to the blue part. The pressure is basically, each of these lines is responsible for showing us the pressure within different parts of the heart. So this black line down here at the bottom is going to be atrial pressure. This black line at the top is going to be aortic pressure. And then this red line here, actually I will write that one in red so that it makes a little more sense with what I'm talking about, is going to be ventricular. All right. So next, I'll also do in red, my bad. We're going to go volume. So this section here is the volume. That volume is the amount of blood that is in. With this volume, it's only showing us the ventricular volume. So this is going to be the volume of blood within the left ventricle. This graph is just looking at the left side of the heart, but you can imagine a similar thing would be happening on the right side. Obviously, the aorta would not be involved because the left ventricle is just pushing to the aorta, not the right. But anyway, this is only looking at the left side, but it makes sense. It's about the same with the right side as well. So that's the volume of the left ventricle. And then we're going to kind of ignore the heart sounds. The heart sounds are basically just what's happening with the graph, but we're going to focus on the EKG instead. I think the EKG is a little bit more informational, and it gives us a good look into the timeline of what is happening. So EKG down here, and then we're going to separate that from... Actually, I'm not going to do that. I don't want to clutter it too much. So the EKG is basically the electrical cardio. It's called the electrocardiogram. What it is basically the electrical current that's happening within the heart. So we can see all these bumps and ridges and whatnot going on here, and that's going to show us the intensity of the electrical signal that is happening within the heart. So this little P wave is going to be our first thing, which is atrial depolarization. And here up at the top, just to make things a little bit simpler as I work through this, we're going to break these down into phases. So it's already separated into 7 phases, and that is pretty much how I'm going to keep it. So the first phase is really going to be atrial depolarization. So first, let's start by looking down here at this P wave. We see the little bump, so that tells us that the heart is sending an electrical signal. It's depolarizing the atria. As the atria depolarizes, we can go up and we can look at the volume of the left ventricle. So you may be asking yourself, why does the volume go up if the atria is the one that's contracting, not the ventricle? The reason this is happening is because as the atria squeezes, it's pushing blood into the ventricle. So if you think about the pathway through the heart, it goes from the atria to the ventricle. So when it squeezes, it passes through the valve and into the ventricle. So that's what this little part is going to be here. That is going to be the atria pushing the blood into the ventricle. Going up to the next part, we can look at the pressure. And keep in mind, these are all happening at the same time. So just after we see on the EKG that it depolarizes, just after, we see a change in not only the atrial pressure, but also the ventricular pressure. The atrial pressure is happening because it's squeezing. So think about it like, you're squeezing something, you're putting pressure on it. As the atria is squeezing, it's putting pressure on, or the atrial muscles are squeezing, it's putting pressure on the chamber. The blood is squeezing into the ventricle. So that's why we see the increase in both the atria and the ventricular pressure, because the pressure goes up in the atria because it's squeezing, and then the pressure also goes up in the ventricle because the blood is filling it. So blood filling and the actual muscular contraction will both contribute to the pressure increasing. So that's going to be the first phase done. So next, we're going to look at the second phase. This one is going to be called isovolumetric contraction. I don't really have room to write that up here, but we'll just go iso right here. So keep in mind, or think about isovolumetric. The volume doesn't change. Iso does not change. It's isolated. So when you look here, that makes sense. The volume's not changing. It's staying the same. Starting from the bottom from the bottom to the top so that it makes a little bit more sense, just like I did the last one, we're going to see the QRS complex. The QRS complex is ventricular depolarization. So the spike in electrical signal for this one is much bigger because the muscle is a lot bigger. The electrical signal needs to be a lot stronger so that the muscle contracts harder and sends more blood, because the left ventricle is going to be responsible for pushing all of the blood out to the body. So it needs a lot stronger of a contraction. So that's why the spike is going to be a lot bigger than the P wave and a lot quicker too. It's happening really quick, really hard, sending the blood out to the body. But not yet. Right now, we're in isovolumetric contraction. So the heart is still squeezing, or the ventricle is still squeezing, but the valve just hasn't opened yet. So looking up here, we can see the pressure start to rise. The pressure is rising a lot here because the ventricle is actually squeezing, but it hasn't surpassed this point yet. So the valve is not open. The blood is still contained within the actual ventricle, but the pressure is rising because it is contracting. Now, looking at the third, this one is going to be the first part of our ejection phase. So I'm just going to write ejection, if I can fit it. Ejection, that's the best I can do. Bear with me. 3 and 4 are going to be both of our ejection phases. 3 is rapid ejection, and 4 is going to be our reduced rejection. So rapid ejection is just, it's happening faster, and then reduced ejection is when it's happening slower. So we'll go back down to the bottom, look at the EKG. It has depolarized. Nothing is happening in this part, but we're still riding off of the depolarization and the contraction that's occurring. So keep in mind, the depolarization isn't showing the actual contraction. It's just showing the electrical impulse that's happening just before the contraction. So this big spike is happening. We then do the isovolumetric contraction, and then the pressure gets high enough to where it blows this valve open, and the blood actually begins to flow out. So here is where we get to see our first big change. The left ventricle blood volume starts to drop rapidly. So why is this happening? the blood pressure is dropping, or the volume is dropping rapidly, but the pressure is going up. And that's because the ventricle is just squeezing harder. That's literally it. It's just squeezing harder to get the blood out into the aorta. So even though the volume is dropping, the pressure is still going up here. So next, also we can see in this part as well, the aortic pressure is rising, because that's when we start to see the blood shooting out of the ventricle and going into the aorta up here. So we see the aortic pressure rise, ventricular pressure is still rising, but the volume is dropping in the ventricle. So next is going to be our reduced ejection phase. Blood is still coming out of the ventricle, but it's coming a lot slower. And we see the pressure start to drop off a little bit here in both the ventricle and the aorta. And that's because not as much blood is being pumped into the aorta. And the ventricle is beginning to stop squeezing as hard as it was. So the pressure is letting go a little bit. The blood volume is dropping. That's pretty much why we see those changes here. If you notice, down here at the bottom, we see the next little wave on the EKG. That's our T wave. T wave is going to be ventricular repolarization. So it's when the ventricle is basically preparing to contract again. So it's relaxing at this point. So that's when we see a very steep drop-off. After this next wave fires on the EKG, we see a very steep drop-off in pressure right here. And that's because the ventricle is starting to relax. So next, the next stage that we get into, stage 5, is going to be isovolumetric isovolumetric relaxation. So I'm going to go and put iso again, but this one is going to be iso C. This one's going to be iso R. Isovolumetric contraction and isovolumetric relaxation. There's no big change that's actually occurring in the ventricle volume, so it's just going to be flat. But the pressure is dropping off in the ventricle because all of the blood has been expelled from the ventricle. So now we're just at a flat line here. But if you notice right here, the aortic valve closes, which means that the ventricle is about to be ready to fill back up with blood. So next, we're going to get into the 6th phase, which is going to be the first of our filling phases. There's nothing going on in the EKG here, and that's because everything is still relaxed. Nothing has contracted, nothing is occurring there. But we do see that the ventricle starts to fill up with blood. So the blood volume rapidly in the 6th phase, rapid filling, we see the blood volume start to go up quite a bit. And we just see a slight rise in pressure because the ventricle isn't actually contracting yet. Nothing's happening musculature-wise. It's just slowly filling up. So we just see a slight increase in pressure there. You might notice that the aortic pressure kind of rises and then slowly trails off as we're going through the filling section. So why is that happening? Because the ventricle is filling. Why is the aorta not filling? Well, it's not filling because it's already been filled. The ventricle is already contracted. It's already pushed the blood out to the body. And now the pressure is just trailing off. The blood is flowing off to the body, and the pressure within the aorta is slowly dropping, slowly going down here. And this, think about, we're going to get back to our baseline over here on the left side as it drops off back down to where it started before. The next part, and the last part, is going to be our reduced filling. So you can kind of think of that, just how we have the rapid and reduced ejection, we're also going to have rapid and reduced filling. So the reduced filling is going to be the same thing essentially as the rapid filling. It's just happening slower. Most of our blood has already flowed from the aorta into the ventricle, and so we just see a slow increase. We also see a slow increase in pressure, and the reason it's going up is because the blood is filling up. Pressure is increasing as the blood fills up, and I'm going to show y'all one other little thing that I kind of forgot to go over here. So we see this little shape happening here in the third and fourth phase. We see the atrial pressure, it kind of spikes. I'll try to do a little highlighting here. Spikes, drops off, and then it kind of slowly rises again. So the reason that it's going to spike right here is because as this ventricle is squeezing super hard, pushing all the blood into the body, the valve of the atria is gonna fire back. It's not gonna open because it only opens one way, but the pressure, the immense amount of pressure from the ventricle is gonna force that valve kind of back onto itself. So the pressure is gonna increase because the space within the atria is being filled by the valve backfiring. So that's what this little increase is for right here. And then as the pressure goes up, we see that it slowly rises here. And this is slowly rising because the atria is actually filling and it's preparing to push the blood back into the ventricle. So the pressure is rising, atrial pressure is going up. Just before this happens here, just before the ventricle actually fills with most of the blood. So atrial pressure goes up, drops off. Once this drops off, that's showing us that the blood is being pumped into the ventricle out of the atria. And then that's pretty much it. Once this is all done, it just loops back around and the same thing repeats. So once you've gone through all of your phases, you've gone through ejection, you've gone through filling, you're going to hop back and you're going to do the same thing again. And it just goes over and over and over. However, there are some things that can complicate this process. And the one that I'm going to be talking about today is going to be atherosclerosis. Alright, so away from the Wiggers diagram, just for now, we're going to be talking about atherosclerosis, which is basically a plaque buildup within the arteries. So I'm going to draw our little artery here, big artery, I guess, our big artery here. With atherosclerosis, what is going to happen is there's going to be a plaque buildup. So plaque is building up. Actually, I'm going to do that. Sorry. I'm going to do that in a different color. We'll do that in red. Bad. It's red. Plaque builds up within the arteries. And it's basically going to restrict the blood flow. So there's our plaque. And here's our blood flowing through, flowing through, flowing through. But then, as the plaque builds up, it gets harder for the blood to flow. When the artery is not clear, the blood is going to have a harder time flowing, and it's going to make a lot of the processes within the actual Wiggers diagram harder. It's not ideal for blood to have a blockage. It's not supposed to have a blockage. So with atherosclerosis, when the blockage is happening, it just makes things a little bit more complicated, which I will show y'all. So looking at some of the changes that occur from atherosclerosis, we're going to get our big blood vessel out of the way, and we're going to look at some of the changes. So the first one is going to be an increase in aortic pressure. An increase in aortic pressure. I'm also going to make my font just a little bit smaller here. There you go. Okay. Okay. So the reason that this is going to happen, basically the plaque stiffens the arteries, makes them less elastic, and that kind of just increases the resistance. Also called afterload. Which y'all might know it as afterload. Because the arteries are harder, they're less elastic, the body or the heart basically has to overcome more pressure, and so we're gonna see on the Wiggers diagram, we're gonna see the aortic pressure rise. So we're gonna see a higher peak in the aortic pressure. So instead of, it might normally kind of look like this, it might be like this instead. That's basically because of the plaque that's building up here. The heart has to overcome that excess pressure that's built up, and so the aortic pressure is going to be higher. So the next change that's going to occur, we're going to scroll down, and we are going to see an increase in left ventricular pressure. Basically for the same reason that the aortic pressure is going up, the left ventricle pressure is also going to have to go up. The heart's going to have to squeeze a lot harder, like I was talking about with the Wiggers diagram. It's going to squeeze, but instead of the normal squeeze where there's no resistance, now there's that extra resistance, and the squeeze is going to have to be a lot harder. Maybe not a lot, but it's going to have to be harder. So, like I said before, it might normally, pressure's high, left ventricular pressure is high always, but it might be even higher after. In order to push through the narrowed arteries, the left ventricle is going to have to generate a lot more pressure, and that basically raises the peak systolic ventricular pressure curve on the diagram. So that's what we're going to see here. The diagram is just going to be altered slightly. Just like the aorta, we're going to see a pressure increase. So next, for number 3, we're going to see a decrease in stroke volume. Stroke volume is basically the amount of blood that the body is able to pump out. So it's the efficiency of the heart at pumping blood. So typically, in a healthy heart, you're going to have a higher stroke volume. It's going to be able to empty out, really squeeze out that left ventricle. So if we were looking at the Wiggers diagram, we would see, we're starting here at the top. This is blood volume decreasing. But after atherosclerosis, with less efficient pumping, it might not empty quite the same way. So it might be a little bit slower, and it might be, that actually does not look much different. Hold on. Might be a little bit slower, and it might be a little bit less. So we're just going to it's going to reduce the efficiency all around within the heart. If it's not able to pump as much blood out, that means the heart is just going to have to work harder to get the same thing done as it would with a higher stroke volume. And that should be it for the changes that occur with atherosclerosis. So because of the plaque buildup, we just overall see the heart having to work harder to do the things that it would normally be able to do a little bit easier before. Overall pressure increases, and like we would see in the Wiggers diagram, those graphs are going to spike a little bit higher. Pressure increase in the left ventricle and decreased stroke volume. And that is it for the Wiggers diagram. Let me draw a little smiley face to show that I'm done here. That is it. Thank you for watching.